Namaste. Today we will discuss about the shock expansion method, right? So far we had a discussion on the various surface inclination methods that you know already, starting from Newtonian method, right? And then modified Newtonian method, right? Then Newtonian Bussmann method, and then we had a discussion on the further approximate methods like Newton wedge and right, I mean a tangent wedge and tangent cone method, right? So today what we will do is like we will proceed further with the shock expansion method. Okay, so shock expansion method is also one direct method, but it is not like a tangent wedge or tangent cone method. It can be justified theoretically, right? So I acknowledge John D. Anderson's hypersonic and high temperature gas dynamics, right? This is the text we are following in this course. So out of all the surface inclination methods discussed so far, we know that considering the Newtonian method, right? So in the Newtonian method, if you know the inclination angle theta, then you can calculate whatever you want, right? Say, for example, if you know the theta, then you can calculate Cp, that is equal to 2 sine square theta, right? So if you know theta, you can calculate Cp, and if you know Cp, you can calculate further Cl, Cd, and L by d. So like that it goes, right? But the tangent wedge method or tangent cone method, that requires a local surface angle, right? But that angle should be definitely less than the shock detachment angle, right? Because the shock detachment angle is calculated at the nose, right? So for a given Mach number, we calculate all those. So tangent method and tangent wedge method and tangent cone method has a limitation, right? Also, tangent wedge and tangent cone method does not have any theoretical background, right? So surface inclination method in this shock expansion method will be an interesting method, right? Which has a theoretical background. Now, so in the case of Newtonian theory can be applied to even for a blunt-nosed body, but tangent wedge and tangent cone method has a limitation that it should have a sharp-nosed body. Do you remember, if it is a sharp-nosed body, so if this is a sharp-nosed body, then only you can draw an equivalent tangent, right? So tangent, and then you can draw the shock, right? So you can consider this as theta and this as beta, even though the real shock forms in this way, right? So do you remember that we have discussed that there is a body shock, right? So this is called body shock, right? This is body shock, and this is the wedge shock, and this is the deflection angle. So the limitation for the tangent wedge and tangent cone method is that it should have a sharp nose, right? But in the Newtonian method, it is not the requirement, right? So again, now shock expansion method can be applied to the sharp nosed body and with the attached shock, right? But in the case of tangent wedge and tangent cone method, we don't have any theoretical justification, but in shock expansion method, we can have the theoretical justification, right? So let us look into the shock expansion method. Let us consider a hypersonic flow over a sharp-nosed body. Okay, so here it is a sharp-nosed body. So let us assume that it is a two-dimensional body, right? So let us say that this is a two-dimensional body. And see here, you know, this nose angle, say this nose angle is considered as theta n. And our ultimate goal is to calculate the parameter at the point I. Say we are interested to calculate the pressure at point PA. Let us zoom this nose section, right? And in the nose section, you can see this is the body, right? So this is a body. So this theta n is an wedge angle. We can say that the semi-wedge angle or whatever it is, right? So when you consider only the nose, we can assume that this is a wedge. Okay, even though it is not a wedge when you consider the whole body, but in our case we consider this as a wedge when we zoom or when we see this particular nose, right? So when you zoom only this particular part, we can say that this can be considered as a wedge, right? So here wedge pressure, so let us say this is Pn. Pn is the pressure near the nose, and Mn is the Mach number in that particular location, right? So the nose makes an angle theta n. Okay, and we know the overview of the flow over the body. So the deflection angle at the nose is theta n, that we know. So in the shock expansion theory, we can say that from the point 1, assume that the nose is a wedge, right? I told you when you expand the nose, when you want to see the zoomed view of the nose, then we can say that this can be considered as a wedge, right? So assume the nose as a wedge with semi-wedge angle theta n. Okay. Then we can calculate the Mach number at the nose and the pressure at the nose, which is behind the oblique shock, right, by the basic exact oblique shock relation. Because you know that here you have a free stream Mach number m infinity, and we know the theta n, and I assume that this is a wedge angle theta n. Then I can calculate the mn, which is the Mach number behind the oblique shock, and Pn is the pressure behind the oblique shock. If we know the Pn, we can calculate Cpn, right, coefficient of pressure. Now let us consider the local Prandtl Meyer expansion along the surface downstream of the nose here, right? So let us consider the local expansion, right? So we can consider the downstream of the nose having a local Prandtl Meyer expansion. So our ultimate aim is to calculate the parameter, that is pressure at point I. Now let us consider the ith point on the surface makes an angle theta I. Okay. So nose makes an angle theta n, and at the point I, it makes an angle theta I, and the pressure we want to calculate on that particular point I is Pi, right? So so if we want to do this, first we need to calculate the Mach number at the point I. Say for example, if we know the Mach number at the point I, then we can calculate the pressure at point Pi, pressure at point I, right? Now Here, surface pressure from a Prandtl Meyer expansion, right, at a local point I, the expansion angle is del theta is equal to theta n minus theta I, right? We have considered this as a Prandtl Meyer expansion, and hence we can write del theta can be equated to theta n minus theta I. So we can calculate with this basic relation, correct? So theta del theta is equal to theta n minus theta I, right? So we can calculate. So del theta can be expressed as root of gamma plus 1 by gamma minus 1 into tan inverse of root of gamma minus 1 by gamma plus 1 into mn square minus 1 minus tan inverse of root of gamma minus 1 by gamma plus 1 into mi square minus 1 minus tan inverse of root of mn square minus 1 minus tan inverse of mi square minus 1. So this we already know. This is a standard expression for the Prandtl Meyer function by considering the 2 points, right? So we can calculate, say in this case, you know mn, right? So the only unknown is mi, correct? The only unknown is mi. So mi is the only unknown, and mn is known from the step 1, right? Based on the oblique shock relation, and del theta is known, that you know. The del theta is theta n minus theta I, right? It is a geometric quantity. This can be calculated simply from this picture. If you know theta I and theta n, you can calculate the del theta. How we know the ratio of the gamma, right? So we can say the specific ratio of gamma is equal to 1.4. We can consider this particular table in the Prandtl Meyer function, and we can calculate mi directly if we consider 1.4 table instead of solving the equation, right? Because we know already it is solved very nicely and the full table is given for the Prandtl Meyer expansion. Right? So mi can be calculated. Right? Once mi can be calculated, then by considering the isentropic flow relation, Pi by Pn can be calculated. So Pi by Pn is equal to 1 plus gamma minus 1 by 2 mn square by 1 plus gamma minus 1 by 2 mi square the whole power gamma by gamma minus 1, right? So now in this expression, you can calculate Pi, right? Because mn is known, mi is known, and Pn is known. So from the Pi, we can calculate whatever we want, right? Now let us have a discussion on the results, right? So this is one results given for the shock expansion method by considering the 10% thick biconvex airfoil, right? So this is for biconvex airfoil. We have an result by characteristics and shock expansion method. So the point is that there is an excellent agreement between the characteristics, right, and the CP calculated based on the characteristics and the shock expansion method. So shock expansion method is one good method for calculating the CP. We will have an exercise sometimes by considering this also. Okay. So let us have a discussion. How can we apply this shock expansion method for the supersonic and hypersonic flow, right? So here we made a very strong point that after passing through the attached shock wave at the nose, The actual flow does indeed expand around the body, and this expansion process is approximated by the assumption of the local Prandtl Meyer expansion. Right? So, by that way, we have calculated everything. Once it enters here, right? So, we consider theta n, and this is considered as a wedge initially, right? And we assume that there is some local expansion, and that local expansion is considered by considering theta n and theta I. That expansion expression is given by theta n is equal to theta n minus theta I, right? So it's a simple process, but it has a theoretical background also, right? Now let us consider a supersonic case and a hypersonic case, right? So consider this particular figure. It is like supersonic flow, and this is a hypersonic flow for a sharp-nosed body, right? The sharp-nosed body, and for the supersonic, this is the shock wave, correct? Correct. Shock wave and reflection wave. In this here, this is the shock wave. Right. Now, in the downstream of the shock wave, expansion waves are generated at the surface of the body, and it propagate outwards, right? And eventually intersecting the bow shock wave, right? So these expansion waves reflect on the shock wave, and it also hit the body surface, correct? This wave again hit the body surface, and if you want to calculate something at the point I, the influence of the reflected shock wave will be also there. Correct? So shock expansion theory, because here in the shock expansion theory, we ignore the effect of these reflected waves on the body surface. Right? So you remember, once we calculate the pressure on the body surface, we never consider this kind of reflecting waves. Correct? The reflecting waves also include, it also affects the pressure at point I. So the idea here is, for supersonic flow, the reflection wave again hit the body surface, right? But in the hypersonic flow, the reflection wave hit the body surface, which is really, not affecting the surface. Say, most of the time it will lie outside the body, right? So that is what in the shock expansion theory, ignoring the reflectives effect on the body surface pressure. So we can say that at the supersonic Mach number, right? At the supersonic Mach numbers, the shock angles and the incident and the reflected wave angles are large. So as a result, the reflected waves influences considerably the surface, and also it considerably influences the pressure which we measure on the point I on the surface. But in the hypersonic case, the shock and the Mach angles are much smaller, and the reflected waves propagate much further downstream, right? Much further downstream. Say this is really further downstream, and most of the time it does not hits the body surface. And if you measure the pressure at a point I, will not have the influence of the reflected wave. So as a result, the reflected waves do not greatly influence the surface pressure, right? And mostly we can say that in the forward portion of the body, it will never influence, right? So we can say that at least to this extent, there is like no effect on the reflected shock. Therefore, in the real hypersonic picture, which satisfies the assumption which we make in the shock expansion theory, right? So it will be having a good agreement with the characteristics, right? So if the Mach number is very high, the shock expansion theory predicts better when compared to the supersonic Mach number, right? So I will just go through it once again. So let us consider this two-dimensional body with a sharp nose, and there is a formation of shock. So this is a shock wave. Okay, the shock wave, and the free stream Mach number is m infinity. And when it enters into the shock, then we can consider that it is a local expansion on the surface. So let us consider the zoomed view of the nose, where we can consider theta n as the semi-wedge angle of the nose. Then if you want to calculate the pressure at point I, that is Pi, and the angle which it makes with the horizontal is theta I, and the expansion takes place between this theta n and theta I. So we can write that del theta is equal to theta n minus theta I. So based on the Prandtl Meyer expansion for del theta, theta n minus theta I can be expressed by this equation, right? So in this equation, if you know theta n, and you can calculate mn, right? And mi is the only unknown, correct? So mi can also be calculated using the table, right? Because here you see mi can be calculated directly, right? Because we know del theta, we know gamma. Say, assume that if it is gamma is equal to 1.4, then we can use the same table. Mn is known, only unknown is mi square, right? Here also, it is not L, it is I. So mi is the only unknown. So we can calculate mi. Once you know mi, considering the isentropic relation, we can calculate pi. So once you know pi, you can calculate Cp, right? So by this way, we calculate pressure based on the shock expansion method. So we made a comparison for a biconvex airfoil, and then the same we have considered for supersonic and hypersonic flow. So we found that inside the shock layer, there is a reflection wave also, right? However, in the supersonic flow, the reflection wave affects the body surface and it influences the pressure on the body surface. But in the hypersonic flow, it lies beyond the body, right? So we can consider that this reflection wave will not have any effect on this eye, right? Eye, or at least we can say the forebody. Most of this body does not have an effect of the reflection wave, right? So this particular shock expansion method is very good for hypersonic flow when compared to the supersonic flow, where in the supersonic flow you have an effect of these reflected waves, right? Thank you very much. I stop at this point, right? I recommend you to go through the John D. Anderson's hypersonic and high temperature flows, right? Thank you very much.